All right, hello class. Here we are, a new week. And with this new week brings an expansion on our discussion of Gaussian field theories and linear models. So over the last few weeks, we've really focused in our attention on writing down and exploring a Gaussian field theory for density fluctuations. And this has enabled a fairly sophisticated theory for predicting the structure of simple solutions. We did that last lecture in the context of a hard sphere fluid, a reasonable model for fluids in which packing or repulsive interactions dominate any specific orientational or directional attractive interactions. So it works well for organic solutions and liquids of simple atoms like argon or helium at least away from really low temperatures. And we also thought about embedding solutes in those fluids, and beginning with a discussion of Debye-Huckel theory and moving at the very end of last lecture to a discussion of the hydrophobic effect, a very brief discussion of the hydrophobic effect. We saw how we could take this Gaussian density field theory and use it to predict all of those sorts of behaviors. This week is really meant to expose just how general those ideas are. So it will be the last week in which our discussion is predominantly based on structural quantities, on thermodynamic behaviors or configurational behaviors. In the next few weeks, we'll really be turning our discussion to dynamics, time-dependent responses, and the correlations that characterize them. But for this week, I want to give you two examples of very different sorts of physical systems that we can apply these Gaussian field theory techniques to. This lecture will focus on a more biologically motivated case, in which case we'll consider the fluctuations of a biological membrane, which is reasonably well described also with a specific kind of Gaussian field. And our goal today will be to work out how we can rationalize the emergence of effective interactions, statistical forces, if you will, that arise when you put solutes in this membrane that constrains its fluctuations in some way. Our next lecture will take a similar sort of perspective, but in a physical system motivated not from biology, but from solid state physics, in which case we'll consider how an electron is solvated by a surrounding lattice, and specifically the Gaussian polarization fluctuations that emerge from a dielectric or a polar lattice. So these two lectures today and the next one will look in terms of variables very different, will be motivated from very different sorts of physical or biological questions, but the underlying mechanics, the basic assumptions, the basic technical steps will be largely the same as what we've already encountered. Okay, so that being said, let's go ahead and get started. So today we're going to consider another type of linear model. By that I mean an effective Hamiltonian, which is Gaussian and thus responds linearly to linear perturbations. And we'll specifically focus our attention on membranes. Which in the context of a linear model are effectively elastic sheets. All right, so why might one try to approach this, question of membrane mechanics from a Gaussian field theory? Well, for one, a membrane, if we were going to think about it on a molecular scale, is some bilayer oily parts sequestered away from hydrophobic parts. Such bilayers are made out of fluid-like particles within the plane, which are thus disordered. They must interact strongly to stay condensed and not diffuse away from each other. And so this is really the ideal case for these sort of effective theory approaches that we've been studying. Like a fluid, it's disordered. Like a fluid, it's strongly interacting. This one can think about essentially being a fluid confined to diffuse in 2 dimensions or flow in 2 dimensions, but whose strong interactions essentially allow for in and out of plane motion, in which we'll be able to characterize energetically through some elastic constants. So we are largely going to think about membranes on slightly larger scales than the specific molecular degrees of freedom that make them up. In which case we can imagine that membrane as being essentially infinitely thin, that statement being valid in the limit that the area of that object, of the surface, is much, much larger than its characteristic thickness. This would be an example of that membrane being flat. One of the simplest mechanical actions I could do to that membrane would be to try to bend it. To bend it, I would need to add in some force, and I could characterize the degree of bending with some omega, I'll call the curvature, which in a flat membrane is 0, and in a curved membrane, something less than 0, if it's curved this way. So we're going to think about a lipid bilayer, for example, as an infinitely flat sheet, which really macroscopically we can envision being characterized by some degree of curvature. We could imagine going in and asking for that curvature locally, which from its molecular details, we could imagine computing if we knew where all those molecules were. Curvature is something defined in a spatially local way. So if we wanted to refine this discussion for a connection between the microscopics and the larger scale structure, we might imagine defining some local curvature, really meaning that this W is some local curvature dependent on underlying molecular degrees of freedom. And if we integrate it over the whole area of the membrane, we could arrive at some global curvature. or macroscopic curvature. In which case, really what I mean by these sorts of drawings is that this is W. So if we're thinking kind of macroscopically, thermodynamically, about manipulating a membrane by bending it, we could understand the response of that membrane, how easy it is to bend, through the kinds of response relationships we've worked out previously. Let's imagine we could write down a potential energy function that knew about all of those molecular level details as a sum of all of the complicated interactions, all the interactions that make up the lipid-lipid interactions that hold that membrane together. And add to it a constant force, which is conjugate to the total curvature. Some sort of bending force. So the description here is we're really interested in kind of macroscopic quantities, how much global curvature is generated under the application of this force F of a membrane, which we acknowledge is composed of complicated molecules which interact in complicated ways. Nevertheless, provided that force really enters into the potential energy function in a linearly conjugated way to the total curvature, we could imagine computing a partition function in the presence of that force, which is going to follow the same rules as we've seen before. Namely, that partition function would be related to a partition in the absence of that force, times the expectation value of e to the beta f times the curvature evaluated in the reference. So again, even though this is not a harmonic oscillator, even though it's not a system whose density fluctuations we're interested in, this is a membrane who we want to understand how it bends. The structure of a relationship between a partition function in the presence or absence of the force takes the same sort of form, which implies that if I was to, for example, take a derivative of the log of Q in the presence of that force with respect to beta times the force, I would get the average curvature in the absence of in the presence of the force. That should be clear by just noting that the only functional dependence on F, holding beta constant of Q of F, is in that exponential So thus I would take the derivative of the exponential of beta f times w. W would come out and be averaged. Analogously, just like we have seen many times, if I was to take two derivatives, I would generate the fluctuations in the curvature. So those are exact relationships, but would require us to be able to compute averages in the presence of the force if we are considering only small applied forces we can get around being able to compute quantities in the presence of the force using our linear response relationships. So for example, if f is small, log of q of f can be Taylor expanded. To 0th order, it would be log of q of 0. To first order, it would be beta f, so I expand in the quantity beta f. The first order Taylor expansion correction would be the derivative of log of q with respect to beta f evaluated at f is equal to 0, which I know from this relationship there is just the average of w in the absence of the force. And I could keep going. Let's give myself a little more room. The second order correction would go like beta f quantity squared and have a second derivative, which is just the variance. And the third order would have beta f cubed over 3 factorial, which is just 6. And the third cumulant of the curvature. And that would be good up to f to the 4th. Taking the derivative of this line, with respect to beta f, I know is exactly equal to the average curvature in the presence of the force, and from my Taylor expansion, approximately equal to the average curvature in its absence, plus beta f, the fluctuations in the curvature in the absence of the force. And that would be good to first order in f. And so we have our usual response relationship, now just written in other sorts of variables. In this case, we have just found that the way in which the curvature changes with a force is equal to beta times the fluctuations in the curvature. That mechanical quantity, how I generate a curvature through applying a force, has a name that is often denoted kappa to the -1 and defined as the bending rigidity of a membrane or an elastic sheet. Often it's how the force, the restoring force, the bending rigidity is defined here through its inverse, because it's often defined as the restoring force given an imposed amount of curvature. Now, as should be clear from the truncation of our response, that bending rigidity in principle could itself depend on the force. If I bent my membrane and then on top of that ask for the subsequent differential change of the restoring force with additional curvature, well, that differential relationship might be slightly different than it was if I started at zero curvature. I can imagine if I tried to take my pencil and bend it a little bit from its initially flat state, it opposes that bend with some force, some rigidity. However, if I bend it past a certain amount, I might imagine that it's much easier to bend, for example, than it was initially. We could, using the same relationships we've already just written down, generalize or ask for how would the bending rigidity change with the force, or how do the fluctuations in the curvature change with the force? And that is going to be given by how the fluctuations in the curvature cubed occur in the absence of the force. Provided these are evaluated at zero. So the way the bending rigidity would change depends on the largeness or smallness of the third cumulant of the curvature fluctuations, how non-Gaussian they are, because the third cumulant is identically zero for a Gaussian distribution. The Gaussian is characterized by a mean and a variance only, has no third cumulant. So to the extent that fluctuations are Gaussian, the bending rigidity is independent of the force. That is just a very fancy way of saying that in our initial harmonic oscillator, independent of how hard we push on that oscillator, its curvature doesn't change. The scale of its fluctuations don't change. If we wanted to understand this microscopically, how would we predict the fluctuations in the curvature and thus understand what underpins the rigidity of this membrane? Well, we could write out explicitly what that variance is, given all the way back up here our initial definition of the curvature as an integral over the whole area, the local curvature determined by the instantaneous configuration of our lipid membrane. So explicitly expanding that out, where in the absence of the force, we expect the average curvature to be zero. Those fluctuations are just given by a double integral over the area. The instantaneous curvature at one point in the area of the membrane correlated with that at another point and integrated over all points on the membrane. So this is to remind you that collective fluctuations, the total variance of the curvature, the net curvature of a membrane, is given by a couple integrals over a correlation function. Here the curvature correlation function. Driving home the idea that microscopically correlations are reflecting macroscopic responses or macroscopic fluctuations. So if we wanted to then go in and try to compute the response of our membrane to a force or a perturbation of another kind, what we would need to know, what we would need to have information on, is how the curvature locally is correlated in space. So to do that, we would likely need, if we wanted to talk about or ask questions about really fine scale structure on the scale of the individual lipids, we would probably need to devise a means of extracting or approximating those lipid-lipid correlations in where they are in space. We will take a slightly different approach because the sorts of scales, often the sorts of questions people are interested in lipid membranes are slightly larger than the individual lipid. They're interested in, for example, we will consider what happens when we put a protein in this lipid membrane, where the protein is fairly large compared to the size of an individual lipid. So a lot of that structure of the individual lipid-lipid correlations is not really relevant. We can get by with a slightly more coarse-grained view. All right, so that's where we'll head now. Okay, so if I was going to draw a cut through a membrane, it might look something like that. That's looking at it kind of edge on, and on large enough scales that I don't resolve the individual lipids that's making it up. So I can imagine it being infinitely thin. Now let's imagine also that, as we've already been discussing, that membrane is on average flat. But of course, instantaneously, it will have some deviation from a perfectly flat membrane here, showing some sort of nearly periodic mode of fluctuation. And let's define now what it would look like on average. On these sorts of scales, for a membrane which is flat on average, a reasonable way to describe the state of the system is by asking where at each point that membrane is relative to its average position. And if it's on average height, that is uniquely defined by a distance from this average position. Let's call that difference h of r. It will represent the height of the membrane at r above its average position. And for each R, there exists a unique height, the collection of which uniquely determines the shape of the membrane instantaneously. Mathematically, that height could be constructed by looking at each point on the membrane, or each particle that makes it up, asking for where that particle is, and taking that particle's position relative to the reference plane and dotting it in with the normal vector. That then lies orthogonal to the reference plane. This construction, the way I've outlined it here, would say that on average, the height above its reference could be defined by some HR, here set to 0. So the mean contains very little information, the way we've constructed this height field. And so the most useful quantity of low order we could imagine asking for is how the heights are correlated spatially relative to one another. And that will define some height-height correlation function we will define as chi, and should depend on only the difference in the positions that I'm asking about. If I assume that that membrane is isotropic within the plane. So here we've just written down a prescription to take an arbitrarily complicated, atomistically detailed description of a lipid membrane and turn it in or coarse grain it into a height field, and lumped all of the details, all of the difficult correlations, all the different difficult manifestations of interactions into this height-height correlation function. That's where all of the details of interactions reside. Now, as I've alluded to, in lots of cases, in the case we will consider, we're not so interested in lots of the small scale structure of chi, the small or really local correlations. We're interested on a larger scale description, something intermediate between really microscopic and macroscopic. And so what we will do is write down a way to approximate chi in a limit which is valid for considering only fluctuations or correlations on slightly larger scales. So to do this, if we want to work with large lengths, that will be analogous to working with small wave vectors. So it will be convenient to express the height field in a Fourier representation. Where I'll suppress the factors of 2's and pi's in this discrete Fourier transform, just for notational simplicity. That's the height field expressed as a sum over wave vectors. I can do the analogous construction of the chi matrix, the correlation function. It can be expressed in a Fourier series. Now, if we're interested in only the large lengths, that is the same as considering, if we're interested only in correlations over slightly large length scales, that's the same as considering chi only for small wave vectors. So if we were going to take chi, or its inverse, and assume it's analytic, we could expand it as just a series. The 0th order term would be some constant. The 1st order term, let's call it some C1 times K. We have a 2nd order term, C2 times K squared. 3rd order term, K to the 3rd, 4th order term, K to the 4th, etc. Now we have to be a little bit careful because these are vectors. So what we really mean at higher order, you have to think a little bit about. Maybe these are tensor products such that chi becomes itself a tensor. But if the system is isotropic, and thus chi depends only on the magnitude r, not its direction, that also means that the Fourier representation of chi depends only on the magnitude of k, not its direction. So really all of these must not be vector k, but must be scalar k. And in addition, the only way to get scalar, or must depend on only scalar only on scalar functions. To get scalar functions from this sort of expansion requires that we have dot products that turn these vectors into scalars. And thus, from isotropic symmetry, all of the odd order coefficients, ones that could not be decomposed into dot products, scalar products, must be 0. So C1 must be 0, C3 must be 0, chi must be expandable as an even series in K. That would provide us with an effective Hamiltonian describing the statistics of the Fourier representation of the height field, given by a sum of these modes. If we wanted a Gaussian approximation, that would be bilinear in h of k with some chi inverse describing its fluctuations, which in this large length scale isotropic limit is determined just by a few numbers, some C0, a C2, and a C4. So that is an effective description of the fluctuations of the membrane, assuming Gaussian statistics. So here's our Gaussian model. With an additional approximation that we're considering the correlations only on large scales. So we have arrived at an effective theory for height fluctuations in those two limits, in the limits of small perturbations, so a Gaussian field is reasonable, and on large scales such that its correlation, the only correlations we care about are those near k is equal to 0. To get some intuition as to what these terms actually mean, C2, C4, and C0, we could back Fourier transform. So a term that looks like C0 magnitude h of k squared, if I inverse that Fourier transform, would give me a coefficient, call it a. Let's put in a factor of 2. H of k squared would go to h of r squared. So we have a harmonic potential with some spring constant A0. Indeed, we can infer, therefore, that C0 should be 0. Otherwise, we would not have fluctuation about some average position. The 0th mode, if you will, would be free. We would have no control over where the average height was. So physically, we might imagine that this membrane is fluctuating above some substrate that then acts to pin it nearby. All right, what about the next order term? C2 has a k squared, h of k squared. Taking the inverse Fourier transform of that, one could write that as a coefficient, call it gamma by 2, the derivative of h magnitude squared. So this is a term that penalizes gradients in the height field. If you think about a flat membrane having no gradient, something with a little bit of gradient like that, if I looked at the projected area associated with going from a flat membrane to a slightly curved membrane, well, then actually this gamma could be interpreted as a surface tension. It's the energy for increasing the differential area of our membrane. For biological membranes, the surface tension is often quite small and, in many cases at equilibrium, exactly 0. All right, what about the final term, C4? Goes like K4. Inverse Fourier transforming that, we'd have to get 4 derivatives that are independent of direction. we could take two gradients of h of k, take its magnitude, defining a coefficient up to a factor of a half. We would identify this as kappa. This is actually the way to compute the curvature rather than the differential area, is by taking two derivatives in that magnitude, curvature being unsigned in this case. Indeed, for biological membranes, that bending rigidity is often quite large, the most relevant term. So putting this all together, for biological membranes, for elastic sheets, we would have a effective potential acting on the height field given by 1/2 an integral over all space, h of r squared times a over 2, a naught over 2. Let's write this a little more carefully. A naught h of r squared, pull the 1/2 outside, plus kappa and the curvature of the height field. So that's our effective Hamiltonian, again, constructed by first coarse graining the system into a height field and considering Gaussian fluctuations on slightly large scales. This has actually got a name. It's called the Helfrich Hamiltonian. First motivated or postulated by Helfrich in 1977, and really is a canonical model for considering biological membrane mechanics. Now that gradient makes this look a little complicated, but really this is just a Gaussian Hamiltonian. It's bilinear in H. And as such, the tricks that we've used to work out the response and the statistics, the correlations of a Gaussian field can be brought to bear on this problem too, on this system too, described by this model. So rather than thinking about the membrane or how you might perturb it locally with some specific structured force, which one could do, one could imagine asking for, applying a pattern force and seeing what the membrane does. Maybe that force is localized, maybe it's periodic. One could think about those sorts of different things. We will consider a kind of biologically relevant question associated with if that membrane, how that membrane might be tethered through receptors that were mobile. And in such cases where those receptors are mobile, how those receptors might arrange themselves due to the effective interactions that the membrane generates between them. Okay, so the picture first that we have in mind. So we have some substrate. Let's not color it blue. And on that substrate are some mobile linkers. At position R1 and R2 that can bind to our membrane. If they bound, that membrane then would be forced to have very specific heights. So unbound, the height can fluctuate. If bound, the height is therefore pinned at a specific location, the location of that binding site, with a height specified by how tall those linkers are. Let's call the instantaneous separation distance between linker 1 and linker 2, capital R. And now let's imagine if the linkers are initially non-interacting, but are mobile. How will they eventually arrange themselves? And we will see that by constraining the height fluctuations through this action of binding, that initially non-interacting sites will become correlated, will have an effective interaction that actually drives them to be close. There's an effective attraction between these binding sites generated just through the action of the fluctuations or the constraint of fluctuations of the membrane. This is a very general sort of phenomena. Anytime you constrain a field, you will generate effective interactions between those particles or substrates that are imposing those constraints. This would have been true if we imposed two different excluded volumes in our density field. We would find, though that calculation is a little cumbersome to do, that those effective solutes are attracted to each other just because they pin the density fluctuations of the surrounding fluid. In this case, the pinning of the height field drives these binding sites together. In other cases, one expects similar sorts of behavior. But we can ask questions like, over what length scale do those attractions exist? How strong are they? And all of those are easily answered within our Gaussian field theory. So let's work that out. So we have an effective Hamiltonian. Describing the statistics of the height field. Written in Fourier space as a sum over wave vectors like so. And again, this is our inverse correlation function. Let's include in that beta. Now, if those binding sites impose a value of the height field at the locations of the site, we need to impose constraints, and we can do so using the same sort of formulation we have used in the density field. We can say that the height at position 1, we can reference this to be 0 in this case. Let's introduce a Fourier representation of that delta function with an auxiliary variable lambda 1. And thus, the Fourier representation would be either the I lambda 1, h of R1. So we'll take this form assuming that the binding site is infinitesimal. So unlike the excluded volume constraint in a density field, which existed over a finite region, over a finite volume little v, this is really localized exactly at a point R1, in which case we don't have a whole auxiliary field to integrate over. It is defined only on a point. It will be useful to write out all of this in Fourier space. That's where our correlation function is diagonal. And so expressing that constraint in our Fourier representation, we introduce the Fourier representation of h of k like so. And it will be useful further noting that h of r is a purely real variable to decompose that Fourier representation into its real and imaginary parts. So let h of k be h of k prime plus I h of k double prime, where h of k prime is the real part and h of k double prime is the imaginary part. Thus, the Fourier representation of h of k, or h of r, rather, can be written as h of k prime times cosine r times k plus h of k double prime sine of h of k, sine of k of nr, where now this is over a set of wave vectors that are unique, excluding the negative of a set of wave vectors. So while the first sum is over all wave vectors, k and minus k included, second sum is over just all positive k. Again, this is because the height field itself is isotropic and purely real. So the partition function with the constraint due to our two binding sites denote that QC, that's an integral over our height field weighted by our effective energy function with those two constraints, that at R1 and some R2, the height is pinned to some value referenced here to 0. Introducing the Fourier representation of those constraints, we have integrals over lambda 1 and lambda 2, integral over our height field, and now the Fourier representation of those constraints give me a minus I, a sum over the two binding sites, labeled 1 and 2, their corresponding Fourier, conjugate Fourier variable for the constraints. And now giving myself a little more space. Our Fourier decomposition of the height field into its real and imaginary components. All right, and now this is Gaussian. With some K inverse that we know. That sets the effective variance of our Gaussian field. So we could integrate it out. Let's write out explicitly what it looks like. So under these integrals, lambda 1, lambda 2, dh of k, we have the exponential of minus 1/2 sum h prime of k squared plus h double prime of k squared times our chi of k, effective stiffness matrix, less I, and let's simplify this notation, introducing a c prime of k plus a c double prime of k, where c prime of k has our two auxiliary variables weighted by the cosines of the position of each of our binding sites, R1 and R2. And analogously, the imaginary part is then weighted by the sine of the location of our two binding sites. Like so. Okay, so this is a Gaussian integral. We have Gaussians in the pure real and pure imaginary fields, but they're straightforward to do. Q of C is going to be some Q naught. We still have the integrals over these auxiliary variables, lambda 1 and lambda 2, but now we have weighted an exponential minus 1/2 from the I squared linear piece. And a sum over c prime of k squared plus c double prime of k squared and chi of k upright, as we would expect in our normal Gaussian interval transformation. All right. Now we introduce those real and imaginary components of C's and H's because this simplifies this subsequent step dramatically. Specifically, if I were to write out this term here, c prime k squared plus c double prime k squared, remember, those were sums of lambda 1 cosine k of R1. I will get a lambda 2 squared, sorry, cosine squared kr2. I have from the k double prime lambda 1 squared sine squared kr1 plus lambda 2 squared sine squared kr2. And then mixed terms, lambda 1, lambda 2, cosine kr1, cosine kr2, plus another mixed term, lambda 1, lambda 2, sine kr1, sine kr2. Or putting this together, we get some real simplification. So cosine squared plus sine squared, hey, that's just 1. Cosine squared plus sine squared, that's 1. Cosine x cosine y plus sine x plus sine y, well, that's a difference angle identity.
Sorry, I'm not sure.
Yielding cosine k dot R1 less R2. So bringing this all together, we have lambda 1 squared plus lambda 2 squared plus lambda 1, lambda 2 cosine k R1 minus R2. And cosine's an even function, doesn't matter if we look forward or reverse. That really simplifies our analysis. Now look at this, we have integrals over lambda 1 and lambda 2, which are just Gaussian. We have a lambda 1 squared and a lambda 2 squared, weighted by our chi. And in addition, we have a lambda 1, lambda 2 term. So writing this out, we have QC is equal to Q naught, integral lambda 1, integral lambda 2, exponential of minus quantity lambda 1 squared plus lambda 2 squared, and its variance is the sum over chi of k. In addition, we have minus 1/2 lambda 1, lambda 2, a sum over chi of k. Let's put this down here. Chi of k weighting a function of the distance between R1 and R2. Now, this term, the sum over chi of k, is of course a number independent of k. Let's define that as psi of psi squared. It turns out to be equal to, you go back through your Fourier transform, it's Fourier transforming just that. It's summing over all, in real space that would be like integrating over all of the height correlation function. That's just given that is just, oh, sorry, red again. That is just the total scale of height fluctuations. Integrating over the whole correlation function in real or Fourier space just tells me about the total global magnitude of height fluctuations. That's what we referenced at the very beginning when we were talking about the total curvature of a membrane being given by an integral over its correlations. So that's just a number. This function here is a Fourier transform of a function of a separation distance. If we were to pull that out, so that's let's call the distance between R1 and R2 some capital R, as denoted in the diagram before. Let's define some function psi of R weighted by c squared as this Fourier transform. Inserting what we mean by chi, we have a factor of kbt. Cosine over our A naught plus our bending rigidity k to the 4th. So there's two useful things just to note of this. It's a function of that separation distance. There's an intrinsic length scale that comes out by dimensional analysis of that denominator. So the wave vector to the 4th implies that there must be a length scale that makes that dimensionless, which is given by kappa over A naught to the 1/4. That's going to set, that's some relevant length scale, like what we saw in Debye-Huckel theory. In fact, this integral, this Fourier transform, looks a lot like the integral we had in Debye-Huckel theory, except for we have a k to the 4th and it's pure, and there's a cosine out in front. This turns out to be something that is computable, that Fourier transform is known as a Kelvin function. Asymptotically, it goes like the exponential of capital R minus capital R over LS. Doesn't have a simple representation away from that, but it is just some exactly computable function. I'll sketch it out in just a second. But defining those two things, so now we have a Gaussian integral over lambda 1, lambda 2 with a variance of 1 over h squared. And we have this mixed term, but is linear in lambda 1 and linear in lambda 2. So those are Gaussian integrals we can do. So if we were to do those integrals, we would have a form of the partition function in the presence of those constraints. Have some factors of 2 pi, the partition function in the absence of the constraint, and quantity 1 minus that Cassis squared, this function psi of r squared to the minus 1/2. That partition function then therefore is parameterized by capital R. Capital R is a parameter, it can be any parameter. And thus I can think about the Helmholtz free energy as a function of that parameter R, given by just minus kBt, the log of the partition function. Writing that out, that's kBt over 2 sorry, I missed a 4 there, plus some constant. If the total scale of height fluctuations is small, I can expand that logarithm, yielding, log of 1 minus a small number is minus that small number. So I get, that becomes an 8. And psi of r quantity squared. So what we find now is an effective free energy, an effective reversible work for moving those binding sites relative to each other, which is strictly attractive, kBt psi squared, strictly positive numbers, and the functional form of A of r, if you were to work out what this Kelvin function looks like, so the function of r, looks something like this, where this is in units of that characteristic length, Ls, 1, 2, or 3. So there's a potential minimum for bringing those two binding sites together that is fairly short range and whose scale depends on the temperature and the characteristic size of the height fluctuations of the membrane. So this is an effective attraction generated through the constraints imposed by those binding sites. It's an emergent interaction, starting with no interaction between the sites. They were free to move, that comes from the fact that there are more ways to fluctuate for the total system when those binding sites are sequestered together. From the perspective of the whole system, the free energy is minimized by bringing those sites together, so the membrane will act to bring them together, to aggregate them. In a dilute limit, if we had multiple binding sites where we could neglect higher order interactions between individual binding sites, we would then have an effective set of binding sites all interacting with these pairwise potentials. That would be an effective theory that would dictate the statistics of binding sites as they move through the membrane. Okay, so that's all I have to say about that. So that shows you kind of how we use Gaussian field theory in a very different context than what we've thought about before. Here in the case of membranes, we have introduced a new Gaussian random variable, the height field, and worked out its energetics in some long wavelength limit, in which case the energetics are just given by elastic constants like the surface tension and bending rigidity, and shown how just by introducing constraints, we generate effective statistical forces between objects in those fields. We'll explore this a little further in the next lecture, but for the time being, I hope you all have a good day, and I look forward to seeing you all in the small group discussions.